Hi, my name is Purya Lotfarizadeh, student number 177575. This is MCEN 4008, Finite Element Analysis, Assignment 1. So let's go over the problem statement together. We have boundary conditions imposed by hinge supports at A and C. We have a beam that spans from A to B with a length of 1.6 meters, and there are 8 springs situated along this length at 0.2 meter intervals with stiffness values that correspond to my student ID digits, as you can see in the table at the bottom right. The beam has specifications 150 UB 14.0, and the link has a cross-sectional area of 2 times 10 to the negative 4 meters squared. Both the link and the beam are composed of a material with Young's modulus of 200 gigapascals. So in this assignment, we have to find 4 things: the deformation of the structure due to the distributed varying load, the spring reaction forces, the forces imposed on link BC, and the reaction forces at pin supports A and C. So first things first, we have to declare what material our link and beam are composed of. In the previous slide, it was given as 200 GPa for their Young's modulus, and this is an attribute that's very close and common for steel. That's why we named the material steel. And in the isotropic elasticity parameters, we set Young's modulus as 200 GPa. So for the geometry, we were given that 150 UB 14.0 is the beam specification, and we found that these are the dimensions that the beam would have. And the link has a cross-sectional area of 2 times 10 to the negative 4 meters squared, meaning and knowing that it's a slender beam, slender link, we assume that the length would be 40 millimeters and the width of it would be 5 millimeters. So by default, when we make a line for each body, being the beam and the link, ANSYS Workbench automatically sets those into the same line body. But for ANSYS to treat them differently and based off of their specifications and their geometry, we have to put them into 2 line bodies and set those 2 line bodies into one part. So here in the middle, we have the cross sections, and at the bottom right, we assign those cross sections to each line body, and we were given that. The model has 8 springs spanning along the length at 0.2 meter intervals. So there's actual support at the BC link, and to allow for deflection studies to be done, we have to allow free rotation about the z-axis in the setup. So we had to do some coding to simulate the distributed load. The first section of the code declares the beam length and the Q value. The second section gathers idea of elements situated along the length of the beam into an array, and the last part computes parabolic distributed loads at each selected element from the array, and it clamps negatives to 0 and applies varying distributed load and outputs at the applied loads on the element. A mesh resolution of 0.1 meter was implemented for the beam and link. We could have used 0.2 meters for it to calculate at every spring's location, but we assumed that this might increase the accuracy of the results. So for the results, we have total deformation of 0.0105 meters, which is the max, about the middle section of the beam, and the minimum is at the top section of the link, hinge C. For directional deformation, we have the minimum situated in the middle, roughly, and the maximum, as you can see, situated there. And it's 8.035 times 10 to the negative 5 meters. So the spring forces were found and plotted into this graph, and this lines up with what we assumed, because the stiffness values that I got based off my ID digits are the highest at K6 and K4. And the distributed load is also the highest around the middle section. For assessment of link BC forces, we have shear forces, given as about 55,000 maximum. The bending moment, which is the follows the opposite trends along the beam, with shear forces being low about the middle and bending moment being at its maximum along the middle. Then we have torsional moment, which is about as high as at where the link and the beam are joined at section B. So for reaction forces, we have overall 77,137 newtons for reaction at hinge A, and the moment is about 8 times 10 to the negative 7 Newton meters. For reaction forces at C, we have a force reaction of 76,779 newtons total, and we have a moment of 4.17 times 10 to the negative 8 as the moment total. And you can see the directions that they're pointing to. Thank you for listening.